We've been throwing around some words here that we really need to define a little bit better. Accuracy and precision are two terms that are often used interchangeably, but are really two different things. Accuracy is the term we use when we're talking about how close you are to the correct answer. In our measurement lab, we define the slope of the line to be pi, and we know its specific value. We can look that up. Our value was pretty close, but not quite exact. So we did a percent error to determine how accurate our data really was. Precision, on the other hand, is how close our results were to each other. Go back and look at the data points. Were they far off from the best fit line? If they were clustered in a similar area, then the data was precise. But if they were scattered all over the place, then they were not precise. So let's look at a few graphs to see if we can visualize this a little better. This first graph looks great. A nice straight trend of our data that isn't too far off from our best fit line. The intercept goes through 0, 0, just like we would expect it to. So this graph shows data that is both precise and accurate. This second graph is all over the place. We can draw a best fit line, but that really isn't what it is. Only a couple of the data points are anywhere near what we were trying to define as our general trend. So this graph is neither accurate nor precise. At first glance, this last graph doesn't look too bad. All of the data points form a general trend, and we can draw a best fit line that appears to give us a nice relationship between the variables. If we look closer, however, we notice that the y-intercept is not at the origin. Should it be? Well, if we have a diameter of 0 centimeters, we don't have a circle. So how can we have a circumference? Since our data closely follows that best fit line, we can say we were pretty precise in our measurements, but at the same time, we can't say that we were accurate. The reason for this is all of those data points are off, but they're off by the same amount. So we were consistent in our wrongly measured data. It just means that we were consistently wrong in our measurements. This is the graph we get a lot of times when we start measuring from the end of the ruler instead of where the 0 mark is located. So again, you can have data that is precise, but not accurate. Precision ultimately comes down to the tool that you use to do the measuring. We can look at this particular ruler, take a measurement, and record in a number of different ways. One person can come in and record the measurement at 8 centimeters. Would this person be wrong? Not really. You could argue that the measurement is an accurate one. Say someone else comes in and now says, wait a minute, our ruler has little markings on it, and we could record it as 7.9 centimeters. Is that person more right? Not necessarily, but 7.9 centimeters is more precise measurement than 8. Now, what if someone else comes in and records the measurement as 7.91 centimeters? Is this still accurate? Yes. He has estimated in between the numbers there, so is that okay? Sure. He can make a legitimate estimate of where in between those two markings the actual measurement lies. So he's being even more precise with his recorded measurement. All right, now someone comes in and records a measurement of 7.91234. Can we use this number? No. Anything after the 1 in our measurement now is just a guess. We can estimate the 1, but anything after that we are just making up. So for a ruler like this, the most precise measurement we could record would be the estimation in between the millimeters. What if we had a ruler that only measured in centimeters? Which measurement would be the most precise? Since we would be estimating in between the centimeters, we would only want to record the measurement to the nearest tenth of a centimeter. So 7.9 would be the most appropriate for this scale. Now, what about the inches thing? Well, inches rulers typically are not marked in tenths. They are marked in fractions. So if we were to record this measurement as precisely as we can, we would need to figure out which fraction we know for sure. The big line there just before the arrow is halfway in between the quarter inch, so it represents an eighth of an inch. That would mean the smaller line to the right is the 16th of an inch. Since the measurement falls in between, we would want to record the measurement to the nearest 32nd of an inch. So the measurement falls about halfway between 2/16 and 3/16, which is halfway between 4 32nds and 6 32nds. So the measurement we would record would be 3 and 5 32nds inches. Now, as you can imagine, the math with this would get a little bit ridiculous, and that's one of the reasons that the metric system is so popular. Now, how precise can we go? The Laser Interferometer Gravitational Wave Observatory is a large-scale physics experiment and observatory that is used to detect cosmic gravitational waves. Go look that up. It's amazing. This instrument consists of huge laser interferometers located hundreds of miles apart, and it is capable of measuring down to 10 to the negative 19th of a meter. So imagine measuring the distance to the sun to the precision of only being off by the width of a human hair. That's as precise as we can go. Now, obviously, we don't have that available for us to use to measure things, but we don't really need to.